Let's go over probability, combinations, and permutations. We're going to look at some common problems in the homework set. Question 2. A special deck of cards has 5 green cards and 3 yellow cards. The green cards are numbered 1, 2, 3, 4, and 5. The yellow cards are numbered 1, 2, and 3. The cards are well shuffled and you randomly draw one card. G is equal to a card drawn that is green. E is a card drawn that is an even number. How many elements are there in the sample space? The sample space is all of the possible outcomes. Since we have 5 green cards and 3 yellow cards, we know that the total number in our sample space is 8 different types of cards. So for part A, we know there are 8 elements in our sample space. For part B, I want to find the probability of E, and E is a card that's an even number. The probability of E is equal to the number of outcomes that have an even number divided by the number in our sample space. I know the bottom number has to be 8 because there's 8 different types of cards. Now, how many elements are there that are even? We have a 2, a 4 for the green cards, and the yellow cards have a 2 as an even number. So there's 3 possibilities out of 8, and we can calculate what 3 over 8 is to find the probability of E. And that is 0.375. So there's about a 37.5% chance that we're going to get an even number out of this sample space. For question 3, according to Master Foods, the company that manufactures M&Ms, 12% of peanut M&Ms are brown, 15% are yellow, 12% are red, 23% are blue, 23% are orange, and 15% are green. Round your answers to 4 decimal places where possible. Part A, let's compute the probability that a randomly selected peanut M&M is not red. Let's use the complement rule. According to the complement rule, we have the probability of not red is equal to 1 minus the probability it is red. The probability of not being red is equal to 1 minus the probability of it being red. So this is equal to 1 minus the probability of it being red is 12%, so we'll subtract 1 minus 0.12, and this gives us 0.88. So the probability that an M&M is not red is about 88% or 0.88. Part B, let's compute the probability that a randomly selected peanut M&M is green or orange. When I see that word or, that tells me add. When you see the word or, think of the word add. So we're going to add the probability of green, which is 15%, plus the probability of orange, which is 23%. So we'll have 23% plus 15%. That is 38%. But our answer is supposed to be a decimal, so let's write this as 0.38. For part C, let's compute the probability that 2 randomly selected peanut M&Ms are both green. Now when you see the word both, think multiply. I'm going to think multiply. So what's the probability of one M&M being green? That's 15%. So that's 0.15. I'm going to multiply that with another 0.15 because we're saying the next one is also green. So 0.15 times 0.15, and that's going to give me our probability. And that's 0.0225. And so our probability of 2 randomly selected M&Ms that are both green is 0.0225. For part D, if you randomly select 2 peanut M&Ms, compute the probability that neither of them are orange. To do this question, we'll look at the percentage of orange M&Ms. There's 23% that are orange. What's the probability of it not being orange? Well, I can do the complement rule again. 1 minus 0.23 is going to be 0.77. This is the probability of not orange. This is equivalent of for the probability of it not being orange. So we want to find the probability that we get 2 of these. So we're going to multiply 0.77 times another 0.77. This will give the probability of not orange twice. So let's multiply that out. And that gives me 0.5929. So there's about a 59.29% chance or 0.5929 chance that we don't get an orange from 2 M&Ms. For part E, if you randomly select 2 peanut M&Ms, compute the probability that at least one of them is orange. This one's a tricky question, so we're going to actually use part D to answer it. We are looking for the probability that at least one of them is orange. Well, this is actually the complement of the probability that none of them are orange. So we can use part D to answer this question. The probability of at least one orange is equal to the probability subtracted from 1 of none being orange. And the probability of none of them being orange is given in part D. That's 0.5929. So I can use 1 minus 0.5929, and this gives us our number. And so our probability is 0.4071. The probability that at least one of them is orange is 0.4071. For this example, we want to find the probability that if we select a random card, that we will get a 3 of clubs. So we'll look for the clubs, and we're looking for the 3 of clubs, and that's this card right here. What's the probability of that? Well, that's one card out of a total of 52, so we can do division. 1 divided by 52. And that's approximately 0.0192. For part B, we're looking for a diamond or a heart. If you look at all the diamonds, there is a total of 13 diamonds. There is a total of 13 hearts. So we'll do 13 plus 13, and we'll divide by the total. There's a total of 52 cards. So we have 26 over 52, or this simplifies to 0.5. So there's a 50% chance that you're going to get a diamond or a heart. Part C, a number smaller than 6, counting ace as a 1. So the ace is considered a 1. For this question, the ace is considered a 1, and we want to look at all of the numbers that's smaller than 6. So this set is going to be smaller than 6 because the ace is considered a 1. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4. So there's going to be a total of 20 cards that are less than 6. So this is 20 out of a total of 52. And we can calculate that as 0.3846. So we have our probability of 0.3846 for a card that's less than a 6. Question 8. A group of people were asked if some psychics can help solve murder cases. 440 responded yes, and 477 responded no. Find the probability that if a person is chosen at random, the person does not believe some psychics can help solve murder cases. So again, we're going to use our formula. The probability of E is equal to the number of outcomes in E divided by the number of outcomes in our sample space. In this question, we're looking for the probability that the person does not believe some psychics can help solve murder cases. So we're looking for not. So all of the people that responded no is 477. That's going to go on the top. But on the bottom, you have to be careful. You're looking for the total number in our sample space. So I'm going to take 440 and add 477. This gives me 477 on top divided by 917. And that's my probability. It's going to be 0.5202. 0.5202. Question number 14. A pianist plans to play 5 pieces at a recital from her repertoire of 19 pieces and is carefully considering which song to play first, second, etc. to create a good flow. How many different recital programs are possible? We have 19 options to choose from, and we're going to pick only 5. Now for these type of questions, you have to think, does the order count or does the order not count? Well, the person's going to play a particular song first, then another song second, then another song third, and so on. So order counts. If the order counts, this has to be a permutation. If the order counts, this must be a permutation. So I'm looking for 19 permutations of 5 because we have 19 to choose from and we're going to pick 5. So N is 19 and R is 5. So we'll type in 19 P5 in our calculators. Now to do that, you'll have to type in 19 first, so enter 1, 9, then click PRB, so that will show 19, and then you want to select the one that says NPR. Select that option, click enter from there, and you want to enter the 5. So you should see 19 NPR5 on your calculators, then you can press enter. And I got 1,395,360. So there's 1,395,360 different recitals that are possible. So that's pretty amazing. We have over 1,000,000 different recitals possible. And that's just from selecting 5 songs from a collection of 19. For question number 11, how many different 3-card hands can be dealt from a deck of 52 cards? Now we have to decide, does order count? In this case, order does not count. The reason order does not count is A, Jack, and Queen is the same as Queen, Jack, and Ace. So the order doesn't really count in this case. So this is a combination. So we're going to use our formula NCR. In this case, we have N is 52 and R is 3. So we're looking for 52, choose 3, and we'll enter that in our calculators. To do that in our calculators, we'll have to enter 52 first, click PRB, and then scroll to the right and you'll see the NCR button. So scroll to the right, you'll see the NCR symbol. Click that, and then enter 3. After you do that, push equals, and you should get your answer. I have 22,100. So there's 22,100 different 3-card hands that we can be dealt from a standard 52 deck. Let's go over some homework questions from binomial probability distribution. For question number 3, suppose that you're offered the following deal. You roll a 6-sided die. If you roll a 6, you win $14. If you roll a 3, 4, or 5, you win $3. Otherwise, you pay $5. So that means you lose $5. Complete the PDF table. List the X values where X is the profit from smallest to largest. Round to 4 decimal places where appropriate. So we'll start with the smallest value of X, and that's going to be negative $5. Remember, we can lose $5, so we're going to put negative 5. Now, how do we lose $5? Well, we have to roll something besides a 6, 3, 4, and 5. So that's going to be on a roll. That's a 1 or a 2. So if I roll a 1 or a 2, I'm going to lose $5. What's the chance of getting a 1 or a 2? Well, that's 2 out of 6. 2 out of 6. And if you do the calculation, 2 out of 6 is 0.333. So we have a 0.3333 chance of losing $5. Now for the next option here, how do we win $3? Well, I'm going to win $3 if I roll a 3, 4, or 5. So if I roll a 3, 4, or 5, I win $3. Well, that's 3 possibilities out of 6, or just 0.5. So I have about a 50% chance of getting $3. For the last one, I can actually make a profit of $14. That's only if I roll a 6. There's only one 6 out of 6 possibilities, and this is equivalent to 0.1667. So this is approximately 0.1667, and so we have that much probability of getting $14. Now, how do we find the expected profit? Well, we need to calculate the sum of the X times P of X column. So we need to multiply straight across for each one of these. So I'm multiplying straight across. I get this is equivalent to negative 1.6665. Negative 5 times 0.333. It gives me negative 1.665. I'm going to do the same thing for 3 times 0.5. That's going to give us 1.5. And we'll do 14 times 1. And then we'll do 14 times 0.1667. And that gives me a number of 2.3338. Now I can add this up and then we'll find our expected profit. And let's round this to the nearest whole cent. And I got the total is 2.17. So about $2.17 is the expected profit. Again, to calculate this, I just added the column that has X times P of X. That's going to be our expected profit, $2.17. In part C, we have to interpret this. Notice this number is a positive 2.17. So that means that if we play this game many times, we are likely to win, on average, very close to $2.17 per game. Part D, based on the expected results, should you play this game? Well, this game has a positive outcome. We're more likely to win in the long run. So yes, you should play this game. And the best option here is the first one. Yes, we should play this game since the expected value is positive. You would be very likely to come home with more money if you played many games. Question number 4. The student council is hosting a drawing to raise money for scholarships. They are selling tickets for $6 each and will sell 500 tickets. There is one $3,000 grand prize, two $400 second prizes, and 10 $40 third prizes. You bought a ticket. Find the expected value for your profit. Round to the nearest cent. Let's make a table. We'll put x, p of x, and then x times p of x in our table. So we have a couple possibilities. We could win the grand prize, which is $3,000. But remember, we're paying $6 to play the game. So if I win the grand prize of $3,000, I'm actually profiting $2,994. $3,000 minus the $6 I paid. Now, what's the chance of getting the grand prize? There are 500 tickets and there's only one winner. So it's 1 out of 500 chance that we will get that ticket. Now let's suppose we have the second prize won. Well, I paid $6, so that would be a profit of $394 if I won the second place prize. Now what's the chance of getting the second place prize? Well, there's 2 out of 500 chance that we'll get that. And there is the third place prize, which is $40. But remember, if we win that, we're not getting $40. We're getting 40 minus 6, which is $34 profit. And there are 10 of those, so there's 10 out of 500 chance that we can get that. Now, this isn't the only option. We have another option, and that's if I lose. What if I lose? Well, I lose $6. That's going to be negative $6. Here is the first place prize, the second place prize, and here's the third. But there's also a fourth, and that's if we lose our money, we don't get any prizes. So how many losers are there? Well, if I look, there's one person that's going to win the grand prize. There's going to be 2 that's going to win the 2 second place prizes. And there's 10 that's going to win the third place prize. So that's 13. There are 13 altogether that's going to win a prize. So I'll subtract 500 minus 13 and I get 487. So we know there's 487 people that's not going to win anything out of 500. Again, we have 1 plus 2 plus 10, a total of 13 winners. And subtract that from 500, we know there's 487 losers that don't win anything. Let's multiply across. I get 5.988 for the first one. 2994 times 1 over 500 gives me that number. Let's multiply this one. 394 times 2 over 500 gives me 1.576. 34 times 10 over 500 gives me 0.68. And finally, negative 6 times 487 over 500 gives me negative 5.844. So now we can find the total. Remember, the total is the summation of x times p of x. And we're going to add this last column here. We're going to add all of these numbers to find our total. And if you do the math, you're going to get 2.4. Now this is in dollars, so we have about $2.40 of expected value. That means in the long run, I can expect to make more money in this game than I would lose. So in the long run, our average winnings would be 2.40. So definitely we should play this game. Question number 8. 16% of all Americans live in poverty. If 50 Americans are randomly selected, find the probability that exactly 10 of them live in poverty. B. At most 9 of them live in poverty. C. At least 10 of them live in poverty. D. Between 7 and 14, including 7 and 14 of them live in poverty. You can do these questions by hand, but it's going to take a lot of work. So it's better to use the statistics calculator that's provided for you. For part A, I'm looking for the probability that exactly 10. So I'm looking for the probability of x being exactly 10. For part B, I'm looking for the probability at most 9. So that is the probability of x being less than or equal to 9. For part C, it's at least 10. So that means 10, 11, 12, 10 and more. So the probability of x being greater than or equal to 10. For part D, I want to be between 7 and 14. So that's 7, 8, 9, 10, 11, 12, 13, 14 inclusive. So that means the endpoints. So for part D, we're looking for the probability of x being between 7 and 14. So all we have to do is enter our probability, which is 16%. That's P of 0.16. And N is 50. So we'll go to our statistics calculator and try these questions out. Let's try the question now on the statistics calculator. I'm going to enter the sample size of 50. And my probability, I'm going to put here for the probability 16% or 0.16. So make sure you enter it as a decimal. And now for part A, we want exactly 10. So click between, and we're going to make it 10 to 10. That's the same thing as exactly 10. So our probability is 0.1057. That's the answer for part A. For part B, I want to calculate at most 9 of them live in poverty. So that means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 is the highest we can go to. So it starts from 0 to 9. So there's several ways I can do that. At most 9 is equivalent to saying below 10. Because if you're below 10, you're going to be at most 9. So we'll click recalculate, and here is our solution, 0.7282 for part B. Now you can do it a different way. You can also click between, and we're going to count from 0 to 9. That's the same as at most 9, and if you click recalculate, that gives us the same answer. So there's more than one interpretation of how to calculate these probabilities. For part C, I want to look at least 10 of them live in poverty. So there's several ways to do that. So I'm going to put above 9. That's the same as at least 10, because what's above 9? 10, 11, 12. So we're going to click above 9, recalculate, and here's our probability, 0.2718. Now I could also do between. I want to do at least 10, so that includes 10, all the way to 50, and if you click recalculate, you'll get the exact same answer as earlier. So there's more than one way to do it. And part D, we want to be between 7 and 14. That one's pretty easy. You click 7 here, and 14, and that's our solution for part D, 0.6984.